So I'd like to go through our short notes that we've created for Riemann sums as a way of just going over some examples of Riemann sums, how they work, what they are, and hopefully this helps you have a really solid foundation of what a Riemann sum is, because Riemann sums will help us establish a foundation for some of the integral calculus that we're going to be exploring next. So first of all, a Riemann sum fits one or more rectangles beneath a curve and takes the total area of those rectangles as an estimate area for the space beneath the curve. So if we have some kind of curve, like say down here we see we have a curve, we want to figure out what the area is underneath it. It's hard to get just a one clean shape that will help us figure out the area underneath this curve. So the idea is we can take rectangles and we can draw rectangles underneath the curve, calculate the area of each one of those rectangles, and then add them together to help us estimate the area under the curve. And ideally, if we have like a little space here that is underneath the curve that's missing, then hopefully some of the space that's outside of the curve can help fill in those spaces and allow us to get a nice estimate of what the area actually is. Okay, so what I think I might do is go through some examples that are in your survival guide and then come back and look a little bit more at the formal notation of a Riemann sum. Okay, so if you turn to the second page of your survival guide, what we're going to do is we're going to look at this example. So we've got the function f of x equals 2 minus 2x squared, and we're going to look at it on the interval of 0 to 1. And what we want to do is we want to estimate the area underneath that curve between 0 and 1. So in order to do that, what we can do is we can divide this area up into rectangles. And I'm just going to choose 5 rectangles. I'm going to divide this up into 5 rectangles of equal length, equal width. And because the widths will be on my x-axis, I'm going to call this delta x. So the change in x in each one of my rectangles is going to be 0.2, because if I take this length between 0 and 1, well, I know that length is going to be 1. If I divide 1 by 5, then each rectangle will have a width of 0.2. So using those widths then of 0.2, what I'm going to do is I'm going to take this area and I'm going to divide it into rectangles. And then I'm going to calculate the rectangles, or the widths of the rectangles, the areas of the rectangles, 2 ways. I'm going to calculate them using what's called a left Riemann sum, and then I'm going to calculate them again using what's called a right Riemann sum. Okay, so in a left Riemann sum, we approximate the area using rectangles where the height of each rectangle is equal to the value of the function at the left endpoint for each interval, compared to a right Riemann sum, where we take the height of each rectangle equal to the value of the function at the right endpoint of each interval. So I'll show you what I mean by that. So here I have my curve. You can see it underneath here. I've made 5 rectangles, each with a width of 0.2. And for each rectangle, I took the left-hand side and used that to make my height. So here, I calculated the function at x equals 0. I know that that height is 2, and then I made my rectangle for those two, my delta x equals 0.2. For that width of 0.2, my height was 2 all the way across. So there's my, my rectangle. And then I did that again here. So here's, for my blue rectangle, here's my left endpoint at 0.2. I sub that into my function. I get 1.92. So for this entire rectangle, my height of my rectangle is 0.192 for that whole 0.2 width. And then again, for my green rectangle, I've got a height of 1.68 when I sub in 0.4, my left endpoint. Here, my left endpoint of 0.6 gives me a height of 1.28. And here, my left endpoint of 0.8 gives me a height of 0.72. Okay? So what I usually do now is I set up a chart. So this is how I set up my chart. There's lots of different ways of doing this. You can streamline this a little bit more. This is just how I think about it. So I say, okay, well, I've got my partition points for my rectangle. So I've got I call this x naught because it's like my first x value at 0, my x1 at 0.2, my x2 at 0.4, my x3 at 0.6, my x4 at 0.8, and my x5 at 1. So those are my endpoints for my rectangles. I call them partition points. And what I do is then I calculate the height of each rectangle at the given partition point. I know my widths are all 0.2, and then all I have to do to find the area of each rectangle is take my height times it by my width to get my area. So for example, when I have my endpoint at x equals 0, I know my height is 2, I know my width is 0.2, so the orange rectangle here has a width of 0.4. For my next rectangle, I know the height was 1.92. I know my width was 2, so the area is 0.384. So I did this for each one of those rectangles. And one of the things you'll notice here is that I have 1, 2, 3, 4, 5. And for this last endpoint at x equals 1, so this one right here, there is no rectangle that I create because then that would go beyond my interval between 0 and 1. So at my endpoint at at my partition point x5 equals 1, my height is 0, but I have no width, so I don't even write a width there because no rectangle is created at that partition point. So I've got my 5 rectangles listed here. I add them up, and I get my left Riemann sum, because I'm using the left endpoints to calculate my areas, as approximately 1.52. And one of the things I want to point out to you is the concept of overestimate or underestimate. So if I look here, because this is going down, it's a decreasing function, I can tell that all of my rectangles are going to be a little bit more than what they should be. So this is going to be an overestimate because it's it's going over the curve for each one. So my areas here are going to be a little bit more than they should be. So I know that my left Riemann sum for this decreasing function on this interval is going to be an overestimate. Okay? So I'm going to do the exact same thing this time, like I said, with my right Riemann sum, my right side, and it's going to look a little bit different. So if I start with my right side, I'm going to start on this end rather than this end because I'm looking at my right endpoints. So I still have the same partition points at 0, 0.2, 0.4, 0.6, 0.8, and 1. But this time I'm looking at different values when I'm creating my rectangles. So for my first rectangle, I'm going to start at x5 equals 1. And I can see here that the function has a height of 0 here. So for this it's almost like a flat line here. It has a height of 0. It has a width of 0.2. So my first rectangle is going to actually have an area of 0 because of that height of 0. Okay? So then I'm going to look at this pink rectangle, and again, I'm going to look at the right endpoint this time. Well, I know at 0.8, it has a height of 0.72, just like it did over here. And I'm going to use my width of 0.2 to calculate the area of that rectangle to be 0.144. And then I'm going to take my right endpoint from my green, put it up to my curve. I find the height to be 1.28, so my area is 0.256. I do the same for my blue, and I do the same for my orange. So you'll notice when I'm coming at it from the right, when I get to my x naught equals 0 partition point, well, I'm not going to have, because it's the right endpoint, I'm not going to have a rectangle on the left side of that. So in this case, again, there's no width here, there's no rectangle created. So we're looking at different rectangles then to calculate my right Riemann sum, which is approximately 1.12. And you can see how with this decreasing function, the right Riemann sum is actually an underestimate of what the actual area is going to be because of the nature of how we draw those triangles when it's a decreasing function coming from the right. So our left Riemann sum will be an overestimate because they're going to overflow, I guess you could say, the function, and these ones will underflow the function because they're all a little bit less than the function. Okay, so just to kind of compare these two, I've got the same partition points for both, because I chose a constant width of delta x to be 0.2, the delta x's are going to be the same for both. The heights are actually the same for both, but it depends on kind of what direction we're coming from. So for the left Riemann sum, we use the left endpoint to create the height of the rectangle, and for the right Riemann sum, we use the right endpoint to create the height for each rectangle. And because of that, for the left Riemann sum, there is no final rectangle, and for the right Riemann sum, there's no initial rectangle, and we have an overestimate and an underestimate. So hopefully that makes sense, and kind of how we create the chart, how we can use that chart to help us just organize our work in terms of finding the areas. And then we add up those areas to have a left estimate and a right estimate. And now what we can do is we can take those two estimates and we can create what's called a trapezoidal approximation. So the idea is that if I take my left and my right endpoint and I average them together, we can create little trapezoids. So you can see here we've got parallel side, parallel side. I've got my flat line here along my x-axis, but then I can create a slanted line that connects my left and my right. And then again, a slanted line that connects my left and right, and so on. And those trapezoids are found by finding the average of the left Riemann sum and the right Riemann sum. So if I take my left and my right and I add them together and divide by 2 to find the average of those two, in this case I get approximately 1.32. Well, this is going to give me a better estimate, because I've averaged the two, of what the actual area will be. So my guess is that if this is my left, this is my right, if I average those two together, approximately 1.32 is going to be a pretty good estimate of what the area underneath that curve is going to be. Okay, so that's called the trapezoid rule, because it's the idea of taking your left and right endpoints, or your left and right Riemann sums, averaging them out, making visually little trapezoids for each instead of rectangles, and then using that number as a better approximation for the Riemann sum. Okay, so hopefully this gives you a kind of an idea of how we can use now rectangles or sums of rectangles to help us make predictions about areas under the graph. And as you can imagine, here I chose 5 rectangles, but if I chose 10 rectangles or 100 rectangles or 1,000 rectangles, it would definitely be a lot more work down here, but that would allow me to get more and more accurate with my prediction of the area underneath the curve. Okay, so there's one example. And actually, after going through that example, I want to go back to the first page of the survival guide and just talk about the notation. So you'll notice that each time I found the area of a rectangle, I used area of a rectangle equals length times width. And in order to do that, I found my height, which was found by taking a point, or my partition point, subbing it into my function, and then coming up with a y value for that function, and then timesing it by what I created as my delta x. In this case, it was my 0.2. So the area of each rectangle was equal to f at the partition point x naught, or x1, or x2, or x3, or so on, times my delta x. So if we go back to the first page where we talk about notation, hopefully this will make a little bit more sense now that you've seen it in action. So our general notation for a Riemann sum uses that summation formula, or the sigma, to represent a sum, where I take so this would be the right Riemann sum, for example. So the right Riemann sum would be k equals 1 to n, so however many rectangles I created, of f at xk times delta x. And we know that f at xk is going to be the y value, or the height of each rectangle, and we know that the width is represented by delta x. And we found delta x in the example we just did as taking our two endpoints, so b minus a, there should be a minus in there, so b minus a over n, to find a consistent delta x. Now delta x doesn't always have to be consistent. We'll look at an example in a few minutes where it's not, but in the case that we just looked at, it was consistent. Okay, so I'm going to take all of those areas that I found by multiplying the height times the width, or the f at xk times delta x, and I'm going to sum them all up for however many heights and rectangles that I'm creating. So this right here is a summation formula that we can use to represent the Riemann sum. And again, I'm kind of just formalizing now what this means. So when we have a left Riemann sum, the idea is we're starting at x naught, and then we're going to keep figuring out our heights to one less than the actual number of endpoints that I have. So n minus 1. So I'm going to take the sum with my index starting at 0 and going to n minus 1 of f at x at I times delta x. So if I write this out kind of in long form, that means that my first rectangle is going to be height times width, so f at x naught times delta x. My second rectangle is going to be f at x1 delta x. And I'm going to keep doing that all the way up to my second last endpoint because it's on the left, f at x n minus 1 delta x. So with the left Riemann sum, we don't use that last height because that would be the right endpoint, and we only use the left endpoints for each rectangle. So this right here basically means we're taking our area formulas, I've connected it to the notation of our function, add them all up to figure out an approximation for the area. And very similar for the right Riemann sum. So this is our right Riemann sum formula. You'll notice that the index numbers are a little bit different. So instead of starting at x naught, we start at x1 because remember we're using the right endpoints and we don't want that first left endpoint to be there. So we don't need our x naught, but we do need our x1. In this case, instead of going to n minus 1, we're going to go straight to n. So we're going to go straight to our last endpoint because we know that that last endpoint will be the right-hand endpoint of one of our last rectangle. So same formula here. This time, again, our heights just start at x1, delta x plus f at x2, delta x, all the way to that right endpoint, f at x n times delta x. And then we add up all those areas of our rectangles to figure out an estimate for our total area. So this is the formal notation that we use to represent what we just did here in our charts, kind of using more common sense and that idea of area just being length times width or height times width, depending on how we're talking about it. So hopefully that helps you visualize what this notation actually means, because that's half the battle, is just understanding what the notation means. Now, the trapezoid rule, when we look at it in a little bit more formal way, is kind of neat. So the idea is we take 1/2, because remember we found the average, and we take 1/2 of what we get when we add together our left Riemann sum and our right Riemann sum. So when we add these two things together, we are going to get an f naught, and we'll get that one time. So I get, this is supposed, that should say f naught, not f6. It's just a little slip of the pen there. So f at x naught, or x naught delta x. But we're going to have two x1s. And we're going to have two x2s. And all the way up to f at x minus 1. There will be two of them because they show up in each one of the formulas. However, the f at xn times delta x only shows up in the second formula for right Riemann sum. So f at x naught delta x only shows up in the left Riemann sum. Everything in between shows up in both formulas, so I've got to count them twice. And the f at xn x naught only shows up in the right Riemann sum, so I only write it once. So the trapezoid rule is basically saying take your left Riemann sum, add it to your right Riemann sum, and this is what you get when you do that. And then you're going to divide it by 2 because you're finding the average of the two. So this is a kind of like a streamlined formula. Again, the notation incorporated into it that basically summarizes what we did when we took our left Riemann sum, our right Riemann sum, and divided it by 2. Okay, so there's our formula for it. And again, here you can just visualize kind of the left Riemann sum, the right Riemann sum. And then there's another Riemann sum that we can talk about called the midpoint Riemann sum. And we calculate it the same way, except instead of using a left endpoint or a right endpoint, we find the middle of the interval called the midpoint, and we use that number to sub into our formula, our function. get our height that way, and then use our midpoint to help us make predictions about how high each rectangle would be. So kind of three different approaches there that we can use Riemann sums to estimate that area underneath the curve. So hopefully that helps out, helps you visualize the notation here, because it does look pretty complicated when you first look at it, but if you just break it down and think about what each piece means, really it just formalizes what we did in our charts here. Okay, so I want to take you through two more examples of calculating Riemann sums. So this is kind of a neat one. We're going to put a context to it, and we're going to look at a function. Instead of giving it to us algebraically, like we did here, we're going to look at a table of values, so a numerical representation of a function. So in this case, we have a test plane flying in a straight line with a positive velocity, v at t, in miles per minute, and time is represented in minutes, where v is differentiable function on t. So it's important that we know that it's differentiable, because we want to be able to apply this to all the values in between as well. So here are some values between time equals 0 and time equals 40 in this table here. So we've recorded the velocity at all of these different times between 0 and 40. And what we want to do is we want to use Riemann sums. We want to use 4 intervals that are equal in length to help us estimate the total distance in miles that the plane flies during those 40 minutes. So remember, if we have velocity in miles per hour, then the area underneath that function, if we were to graph this, would represent the distance traveled. So if we can figure out the area, or predict or estimate the area under v at t using the values in this chart, then that will help us approximate the total distance. Okay? So we only want 4 subintervals here, and I've got more than 4 subintervals. So what I'm going to do is I'm going to take my 0 to 40, I'm going to divide it by 4, which means that if we're using equal intervals, each interval will be 10 units long, or 10 minutes long, I should say. So here my first interval is going to go from 0 to 10, then I have an interval from 10 to 20, 20 to 30, and 30 to 40. So when I created my partition points, I created one at 0, 10, 20, 30, and 40. And now this is actually going to be even easier for us because we don't have to do calculations. The heights at each one of these partition points are actually given to us straight up in the table. So at x naught, or equals 0, so when time is equal to 0, the height is 7. When time is equal to 10, the height is 9.5. 20 is 4.5, 30 is 2.4. And for the left Riemann sum, the height doesn't matter. We know it's 7.3, but we know that we're not going to be able to create a rectangle on that side of it anyway, so it doesn't matter because no rectangles form for there. I know for each one of these heights, v at t, that my delta t is going to be 10, because that's what we calculated our even subinterval length to be. And so then I can calculate the area of these rectangles. 7 times 10 is 70, and so on. And I get my left Riemann sum to be approximately 235 miles. So if we use the left Riemann sum to predict, we get 235 miles covered by the test plane. I'm going to do the exact same thing this time with the right Riemann sum. So again, I still have my same partition points, but this time the first height doesn't matter because I'm not looking at, if I'm using my right side, I don't have a rectangle to the left of that. So I don't worry about that rectangle there. But I'm going to use these values here. So I get 9.5, 4.5, 2.4, 7.3. I times them all by 10 because my width delta t's are 10s. And when I add those rectangle areas up together, I get my right Riemann sum to be about 237. So these are pretty close together, which is a good sign. And I just want to point out in terms of the units, just to show you why this area gives us miles. If we take our height of each rectangle, and knowing that our height is actually represented by velocity, or our velocity is in miles per minute, our width of each rectangle is time in minutes. So I have miles per minute times minute. Well, the area then, when I multiply those units together, is going to be miles, because the minutes and the time is going to cancel it with the minutes at the bottom of my miles per minute here. So I can see how the units actually just kind of confirm that when I find the area of each rectangle, I'm actually finding a distance in miles. Okay? So finally, I can take that the left, right Riemann sum, the right Riemann sum. I can add them together, divide by 2, and I get my approximation to be 235.5 miles altogether. So this is how I would use my trapezoid rule when I have already calculated my left and already calculated my right. If I hadn't done these two things separately, I could streamline this a little bit. So if I was just asked to use a trapezoid approximation or the trapezoid rule to calculate or estimate my area, I could just do this in one chart. So the idea remember, for the trapezoid rule is you're adding together the left and the right. So I'm going to use those same partition points that I used up here. I'm going to use the same heights and the same widths. And I know from my left, I need my area at my partition point x naught equals 0. And I know from my right, I need my area for my partition point at x4 equals 40. So I'm going to put those two in there. And then for all the ones in the middle, because my width is equal, I'm just going to take them, times them by 2, because these ones are all located in both the left and the right Riemann sum. So I've got my 70 from my left, I've got my 73 from my right, and then I've got my 95 times 2, my 45 times 2, and my 24 times 2, because they all show up twice. And again, I get that same value that I got if I had have done the whole left Riemann sum and the whole right Riemann sum, added them together and divided by 2. So I could do this either way. This is just a quicker way to do it if we haven't already done the left and right, but we wanted to use the trapezoid rule to get a better approximation. Okay? And then finally, and this is actually a really good example where we could use the midpoint Riemann sum to help us make a prediction. And this is actually going to be probably the quickest one. Because of the way that this chart is set up, if I have intervals of 10, this table of values has actually given me the v at t at each midpoint of each interval. So this is actually quite nice to do this. So if I'm looking at this first interval from 0 to 10, well, the midpoint is at 5. So when I have a partition point at 5, I know that my height is going to be equal to 9.2. And when I have my partition point, so I'm just going to zoom out a little bit here so you can see here. So in my second interval between 10 and 20, my midpoint is going to be at 15. So at my midpoint at 15, my height is going to be 7. Between 20 and 30, my midpoint's at 25. So my velocity or my height at 25 is going to be 2.4. And between 30 and 40, my midpoint is 35. So my height at 35 is 4.3. So using those 4 midpoints, I can calculate the height or the velocity, which represents the height of my rectangles at those midpoints. My width I know is still 10, and I calculate my 4 areas, add them together, and this approximation is 22.9, okay, miles. So this basically represents lots of different ways that we can use Riemann sums to help us estimate the distance that was traveled given these velocities clocked at different times within that 40 minutes. Okay? So a couple things that I just want to clear up. So first of all, in the 2 examples that we looked at, the one where we just had a function and we estimated the area underneath the function, and this one here, we actually had a situation where we looked at a velocity graph or velocity table of values and used it to predict distance. We looked at intervals that are equal in width. So here the intervals were all, or delta x's were all 0.2, and here are delta t's were all 10. It works out really nicely when we have our intervals that are consistent. But there may be some times where we have to make predictions when the intervals aren't consistent, or it just works out kind of to be more accurate when we have intervals that are different widths or different widths for each rectangle. So I want to take you through one example of that case just to show you that it's not always the case that we have widths that are equal. Okay, so here is another example. So this example 3, we've got water draining out of a tank at a variable rate, and somebody has taken some data collection up, and at different times here has done calculations about how the rate at which the water is draining out of this tank, and it's in gallons per minute. And you'll notice here that the intervals that my x's are changing are not consistent. So I'm going to start off with my partition points. So partition point 0, 1, 2, 3, 4, and 5. So at time is equal to 0, I have my height is equal to 0, but my width to my next value, if I'm using my left Riemann sum, which is what I've chosen to do here, is going to be 5. So I've got my height at 0, and my width of my rectangle is going to be 5. So my area for my first rectangle is going to be 0. And then I'm going to take my x1, which is going to be 5. And at 5, my height is 5. And to go to my next x value is another 5. So I know that my width is going to be 5 again. So that rectangle is going to be 5 times 5, which is 25. For my next one, so for my x2, I have my left endpoint as 10, which means that my height is 20 right here. But to go to my next endpoint, I have to go 10. So you'll notice here that my width here is 10, not 5. It doesn't always have to be consistent. And this is a case where the data just lends itself to having different widths. So this rectangle is going to be 20 times 10, which is 200. My next endpoint is going to be at the 20. The 20 has a height of 30, so my height is 30, and my width is going to go to my next endpoint, which is this 30. So that's another 10 for my delta x. So I've got 30 times 10, which is 300. And then when I get to my 30, my height is 10 or 15. And then my width of my rectangle to my next endpoint is going to be only 5 this time. So 15 times 5 is 75. And then I know that at my last endpoint, I'm not going to have a rectangle there because I don't have anything to the left or to the right of that. So next no rectangle is formed. So when I calculate the areas of those rectangles, I end up getting 600 gallons. So approximately 600 gallons of water has leaked out between 0 and 35 minutes. And you can see just a little visual of that here. So our first rectangle is 0, and then I have a thin rectangle with a width of 20. Then I have a width of 5. I have 2 rectangles that both have a width of 10 based on my data, and then my final rectangle has a width of 5. So I just wanted to make sure that you know that the widths, it's helpful when they're the same. That's probably the easiest situation, but sometimes we do our Riemann sums calculations when the widths are not the same. And just to go back to those formulas that I showed you on the very first page. On the very first page here, in order to use these more formal formulas, this only works when your delta x's are the same. So I could have used kind of this more formalization of the Riemann sum formula for the first 2 examples that we did, but I couldn't have used this formalized version of the formula with the example number 3 because the delta x's weren't the same. So these would not double up in the same way or work in the same way because the delta x's are all different. Okay, so I just wanted to show you that you can still calculate Riemann sums when the widths are not all the same, but more commonly when we can, we do try to get those widths the same just to make the calculations easier. Okay. Again, just to show you the units here to prove that we did actually find gallons. So if we take this curve, the heights of each rectangle is represented by the curve, which is a rate of the gallons per minute. So my height is gallons per minute. My x's, which is my width, are measured in time, which is in minutes. So if I take gallons per minute and times it by minute, the minutes cancel out, and our area then is a gallon. So the area underneath this curve represents the accumulation of gallons of water that has collected between time is equal to 0 and time is equal to 35 minutes. Okay, so hopefully these 3 examples give you a visual of how to calculate Riemann sums with a function, how to do it within a table, how to create left Riemann sums, right Riemann sums, use the trapezoid approximation, look at midpoints, look at when examples are have widths that are equal, have widths that are not equal. And just as a final kind of two big ideas here, I just wanted to kind of sum this up. We've kind of talked about it a little bit along the way, but you always want to think about whether your Riemann sum is going to be an overestimate or an underestimate. And just to kind of visualize here, whether it's an overestimate or an underestimate is going to depend on whether you're finding the left or the right Riemann sum and whether the function is increasing or decreasing. So if we look at the left Riemann sum, which is pictured in this picture here, if the function is increasing, you can see that the left Riemann sum is going to be below the function. So it's going to be an underestimate when the function is increasing. So we can see that in the pink area here and the pink area here. The Riemann sums are below, the rectangles are below it. If we look at a left Riemann sum when the function is decreasing, you can see that the left endpoints create rectangles that are a little bit higher than the function. So it's an overestimate with a left Riemann sum when its function is decreasing, and it's an underestimate with the left Riemann sum when the function is increasing. And the reverse is true for the right Riemann sum. So here is a right Riemann sum. You can see we've created the rectangles from the right endpoints. So when the function is increasing, you can see that the right endpoints create rectangles that are above the function. So we know that that's going to be an overestimate. And when it's decreasing, you can see the right endpoints create rectangles that are below the function. So we know it's going to be an underestimate. So sometimes if you want to figure out if your estimate is a little bit too high or a little bit too low, think about whether the function is increasing or decreasing. Think about whether you're finding a left Riemann sum and a right Riemann sum and how you're creating those rectangles, and use that to predict whether your function is going to be a little bit higher than the actual value or a little bit lower than the actual value. And the really big idea, I want you to even highlight this in your notes, because this is a big idea that's going to carry with us through as we talk about, as we move into integration. Excuse me. But the area under a curve of a function represents accumulation of the quantity for which the rate is being represented by the function. So when we're working with velocity, for example, the area underneath a velocity curve is going to be an accumulation of the distance traveled. When we're looking at volume, well, we know that, the rate at which a volume is changing, we know that the area underneath that rate function is going to be an accumulation of the volume. So that's a really big idea, because that can help us calculate things that we want to find that are defined by functions that aren't necessarily pretty functions to work with. So the idea that area underneath the curve of a function represents the accumulation of whatever that rate of change is representing is a really big idea that hopefully you will remember as we work through our integration unit. So hopefully this video has given you an idea of Riemann sum. Hopefully this helps you to understand your survival guides, and that you will use this as a reference as you're working through some different problems to practice calculating Riemann sums, and that you have a strong understanding now of how we can use rectangles, adding up those rectangles, summing them up to help us predict area and what those areas actually represent.